Hello everyone! Today's discussion is about momentum and perhaps most glorious, the conservation of momentum. Let's say you play pool and a cue ball strikes other ball rather. Let's say you scatter the ball as much as you want. The total motion of the system still remain constant. This law is the backbone of all, from the collision of two cars to that of two planets. So let us explain in detail how momentum as a quantity resolve lot of imbalance in universe. From ranging small particles to large clashes. We are ready to start.
In this first scenario, one ball is lifted and released, swinging downward and hitting the row of stationary balls. Notice that the momentum from the first ball is transferred through the stationary balls, and the last ball moves with the nearly same speed. This is a clear example of momentum conservation.
Now, we lift and release the two balls. Watch what happens when the two balls collide. Just like before, the momentum of the two balls is transferred, but now two balls move on the other side, conserving momentum.
Next, let's lift 3 balls and release them. Here, 3 balls on the other side move. The total momentum is still conserved and it's transferred from the 3 balls on the left to the 3 on the right.
In every case, whether we push one, two, or all of the balls, the principle of conservation of momentum holds. The total momentum before and after the collision is always the same. This is Newton's cradle in action.
Imagine two toy cars on a smooth surface. Car 1 is moving toward car 2, which is sitting still. Before the crash, car 1 has some speed and car 2 is at rest. This means car 1 has momentum. Momentum is just the speed of something multiplied by its mass. After the crash, both cars move together. Even though car 1 had momentum before the crash, now car 1 and car 2 share the momentum. The total momentum before and after the crash stays the same. This is called the conservation of momentum.
Now, let's imagine the two cars moving toward each other, and they crash head-on. Before the crash, each car has its own momentum, depending on its speed and mass. After the crash, the cars may bounce back, but the total momentum before and after the crash remains the same. The cars transfer momentum between them, but the total momentum of the two cars doesn't change.
So whether they crash from behind or head-on, the total momentum of 2 cars before and after crash stays the same. That's the law of conservation of momentum.
As the volleyball falls, it gains speed because of gravity. When it hits the floor, it bounces back up. But notice something important. The momentum it had before hitting the floor is transferred to the floor, and then the floor pushes it back up with an equal amount of momentum. The total momentum of the volleyball before and after the bounce is the same. This is an example of conservation of momentum. The ball's momentum is transferred to the floor, and then the floor pushes it back with the same amount of momentum.
Just like the volleyball, the rubber ball gains speed as it falls. When it hits the floor, it also bounces back up. But since the rubber ball is lighter than the volleyball, it may bounce higher or behave differently. But the total momentum before and after the bounce is still conserved. The momentum of the rubber ball, just like the volleyball, is transferred to the floor and then pushed back. So no matter what the size or weight of the ball, the total momentum stays the same.
In both cases, the momentum before and after the ball hits the floor is conserved. The momentum doesn't disappear, it's just change form. This is the principle of conservation of momentum.
Now, we drop both balls at the same time. The volleyball falls first, and when it hits the floor, it pushes the rubber ball upward. Here's what happens. The volleyball doesn't bounce very high because it's heavier and has less bounce. but when it hits the floor, it transfers some of its momentum to the rubber ball on top of it. The rubber ball, being lighter, has more bounce, so it gets pushed higher after the volleyball hits the floor. The momentum from the volleyball is transferred to the rubber ball, making it bounce much higher.
In physics, a collision is when two bodies, such as two billiard balls or Newton's cradle ball, forcefully come into direct contact. A smaller mass will collide with a larger mass in the introduction and bounce back. Both masses will continue to gain momentum in the direction of the initial motion if a greater mass is initially approaching a smaller mass.
Two similar objects, such as billiard balls, collide in one dimension in which one is initially motionless or has no mass, and the moving object remains stationary while the other moves at the same pace as the other. The collision in which both momentum and kinetic energy are conserved. The colliding bodies continue to move in the same straight line afterwards.
When the ball is released, it moves down the track and collides with another ball that is set up on an adjustable target support. This is how the collision in two dimensions device operates. A two-dimensional collision occurs when the initial and final velocities are in the same plane.
When there is no coefficient of restitution, or when the amount of respective kinetic energy lost in collision between two moving objects, the colliding particles stick to one another, or kinetic energy is lost by binding the two bodies together. The collision is said to be inelastic. The system often loses its maximal kinetic energy as a result of this bonding energy. In an inelastic collision, the system's momentum is conserved but its kinetic energy is not.
And that's all. Thank you for your attention. We hope you enjoyed our presentation and found it insightful. We appreciate your time and look forward to your questions and feedback.